Okay, today begins our introduction to matrices, which is a lovely little complex piece of maths that comes up absolutely everywhere the further along in your studies you go. So the basic idea of a matrix, which is the singular form of matrices, you've got one matrix or two matrices, is very simple. Let's imagine I want to discuss a direction, okay? I can give a direction in two ways. I can say either go 4 meters. Go 4 meters. And that's all well and good, but that doesn't really tell me much. Go 4 meters where? That way, down there, upstairs. Where am I going 4 meters, right? This here is just a number. 4 is a number. Remember that, note that down. 4 is a number. Now, you may, well, hopefully you're already familiar with vector notation. So instead of saying go 4 meters, you might say go 4 meters straight and then 3 meters to the left. And you might denote that as, well, straight and left, not quite, but up and down, left and right, you might denote as a vector. 4, 3. Go 4, in this case, to the right, and 3, in this case, up. And this is a little bit more exact. And essentially, the idea of a matrix is that we just keep going. We keep adding more and more directions. We keep making this dimension even larger. And then we might end up with something like 4, 2, 3, 1. And this here doesn't really have a exact description. I suppose you could say it's go 4 left, 2 up, 3 down, and 1 across, and that would be pretty exact. But that's not really where we use these things. That kind of use finishes out vectors. With matrices, it's more about being able to represent two-dimensional data in a much larger and more workable place. So this is what we would call a matrix. Although it's important noting that this vector example here is also a matrix. So you have encountered these before, you've just encountered a very small matrix. So a number is a one-dimensional object, it's just got one thing there. A vector is a vector or a matrix, but mainly a matrix, is a two-dimensional object. And you're probably not asking yourself, but if you are there more? Can you go to a third-dimensional object? You can. That's called a tensor. If you don't know what a tensor is, don't worry about it. If you do know what a tensor is, I don't know why you're watching this video. If you're trying to learn what a tensor is while watching this video, good luck. But for now, we're going to stop at matrices. So let's just look at a couple of qualities of matrices, a couple of easier things about them before we get into the real tough stuff. Okay, I'm going to start off with a revolutionary piece of mathematics called addition. And you may be asking why I'm starting with something as basic as addition. It's because with matrices, they don't always add, subtract, multiply, divide, perform normal operations in the way that we would expect. So it's important to be able to realize when they do behave as we want them to, or as we expect them to, and when they don't. So with the case of addition, matrices perform exactly as we would want them to. We simply look at corresponding elements in the table. So the top left and the top left add together. 5 plus 6 is 11. The top right and the top right add together, and that is a 10. Bottom left and bottom left add together, and that is also 10. And then the bottom right and the bottom right add together, which is 3. It's not rocket science, but it's important to just remember that matrices do a lot of weird stuff. Addition is not one of them. Likewise, if this was a subtraction, they would subtract exactly as you would expect. 5 minus the 6, 3 minus the 7, 2 minus the 8, and 1 minus the 2. So it's very, very important to realize or to start taking note of the position of each of the numbers, because it's important that we sync up top left and top left, top right and top right, and that becomes especially true in a moment when we look at multiplication. Now, our first step to matrix multiplication is when we multiply a matrix by a number. And I'm going to stop calling them just numbers now. Whenever we have just a number on its own, a one-dimensional figure, it is called a scalar. Hopefully we're familiar, scalars and vectors. It is just a magnitude, no direction. Now, when we multiply a scalar by a matrix, once again, it performs exactly as we would want it to. This number simply multiplies by all four of these. So I get, in my top left, 5 times 3, in my top right, 5 times 2, in my bottom left, 5 times 6, and in my bottom right, 5 times 1. And it multiplies exactly as we'd like it to, all hunky-dory, all good to go. Okay, now let's move on to real matrix multiplication. A matrix times by a matrix. So, well, we know the drill by now. Top left, we're going to have 1 times 2, and top right, we're going to have 2 times 3. No. Unfortunately, matrix multiplication does not work as we would expect it to. Top left does not multiply by top left, top right does not multiply by top right. Instead, we have to do something rather special and rather annoying. What we need to do is we need to separate each matrix into 2 components. The left matrix gets separated into rows. So that is a row and that is a row. And my second matrix gets separated into columns. That is a column and that is a column. So whenever we're doing matrix multiplication, we always want it to look like this. The left one has 2 rows, the right one has 2 columns. Now, what we're going to do is we are going to, and this is going to be my answer matrix, start off with the top left. I'm just leaving spaces here for numbers so we know where they go. I'm going to start off with the top left. In order to get my top left value, I'm going to take the first number in my first row here and my first number in my first column here, 1 and 2, and I'm going to multiply them together, 2. But wait, you just told me not to do that. Hold on. Because then I'm going to take my second number in this row and I'm going to take my second number in this column and I'm going to multiply those 2 together. And then I'm going to add them. So I'm going to find my first number in this row, first in the column, and multiply them. I'm going to find the second in the second and multiply them. And add the answers and I will get a 2 plus 2. I will get a 4 in this spot. Okay, what about this one? Well, top right. Where's my top right row in this matrix? There's this one. It's the row that contains my top right. So once again, I'm going to be working with this row. And then in this column, in this matrix here, where's my top right? It's in this column. So I'm working with this row and this column. So I'm going to do it once again. Take the first number in the row, multiply it by the first number in the column, 3. Second number in the row, multiply by the second number in the column, 2 times 4 is 8. And I'm going to add them. 3 plus 8 will be 11. Bottom left. What row is my bottom left in? Well, it's in this one. What column is my bottom left in? Well, it's in this one. First times first, 3 times 2, 6. Second times second, 4 times 1 is 4. Add them together, and I'll get 10. I'll write that out fully in a second. And then finally, where's my bottom right? Well, it's in this row. It's in this column. 3 times 3 is 9. That's the first one. Second one is 4 times 4 is 16. And I end up with 4, 11, 10, and 25. And that is my final answer for multiplying these together, which looks deranged. And it's complicated and it's annoying, but we will get used to it. We just need to brute force it one by one, and eventually it will start coming to us intuitively. Now, let's have a look at what I've got here. Well, I've got the same 2 matrices. I've got 1, 2, 3, 4 times by 2, 3, 1, 4. So the answer's the same, right? what did we have last time? It was, I've already forgotten, 4, 11, 10, 25, I think. You can go back, I can't think it was that. So surely it's the same, right? 3 times 3 is, 3 times 4 is 12, 4 times 3 is 12. We can switch them. Well, let's find out. So, in my answer here, I'm going to multiply them. So, top left is going to be this row and this column. First times the first is 2, plus the second, 3 times 3 is 9. 2 plus 9 is 11. Huh. Okay. Well, 11's not 4, and last time it was 4, so maybe I've made a mistake. Let's keep going. Top right is this row again, and this column. 2 times the 2 is 4. 3 times the 4 is 12. 4 times 12 is 16. Well, 16 isn't 11, I think. Okay, I've probably made another mistake. Let's do the other ones. Okay, bottom left, that row and that column. First times the first, 1 times 1 is 1, plus 4 times 3 is 1, plus 12, 13. Okay, but the last one will be 25, and then it will balance out. Bottom right here, this row, this column, 1 times 2 is 2, 4 times 4 is 16. 11, 16, 13, 18. I mean, the 11's the same, it's just in the wrong place, and, 18's kind of 25. Yeah, if you couldn't sense the sarcasm, you cannot simply switch the order of a matrix and expect it to still multiply properly. It is what we call non-commutative. Non-commutative. Something that is commutative, you can switch the order of multiplication, it still works. 5 times 6 equals 30, 6 times 5 also equals 30. It is commutative. But matrices, you cannot swap. The order of the multiplication, the one on the left and the one on the right matters, because the one on the left is rows only, the one on the right, we're only concentrated on the columns. Okay, very last thing, what if the matrices aren't the same size? Well, luckily the same rules still apply. The left matrix, I'm concentrated on the rows, and the right matrix, I'm concentrated on the column, singular, there's only one. Now, this matrix is not going to be a 2 by 2. It's not going to be the same square we've had recently. Instead, it is going to be a 1 by 2. And you'll see why in a second. So, for our top number, we've got, where's at the top? Well, it's this row and this column. So it's 1 times 1 is 1, plus 2 times 2 is 4, that's 5. And the bottom, well, it's going to be the bottom row. There's only one column, we've got to stick with it. 3 times 1 is 3, 4 times 2 is 8. That gets me 11. So they still multiply just fine, but they form a different shape. It's a different type of matrix, simply because we don't have that extra column to play with, so we don't have anything we can put over here. If I had a number over here, I'd be looking for the rightmost column, which doesn't exist. So I can't do it. Okay, very last example, let's switch these around and multiply them. Okay, so let's now flip them around and multiply them. We know the answer is not going to be the same, and let's probably guess that maybe the shape is going to look like that again and see what happens. Okay, so we've got rows in this one and columns in this one. Let's get started. So, first number in this row is 1 times 1 is 1, plus the second number in this row. Okay, well, there isn't a second number in this row. So, what do I do? Is it 0? Is it 0 times 3 and then it's 1 plus 0 is 1? No. This is impossible. We cannot always multiply matrices. Sometimes the dimensions of them make it impossible. If we run out of numbers, so in this case, I need a second number in my row to multiply by this guy here, and I just don't have it. And if I just don't have it, well, nothing can be done. I can't assume it's 0. I can't make up a number to put there. I can't leave the 3 on its own. It's just not possible. As a general rule, the leftmost matrix must have the same number of columns as the right matrix has rows. Here, my left matrix has just 1 column, my right matrix has 2 rows, and unfortunately, the multiplication will not work. So, this has been an introduction to matrices. As we move on, we will start looking at things like inverting matrices, finding determinants, and then also actually using them in modelling and real-world applications, because who doesn't love modelling in pure mathematics?